We've learned a lot of integration techniques, and we need to add some more to our list to deal with some integrals that involve products. Integration by parts works very, very well for products. You have two functions multiplied together. Now, usually they're a mix. They're a mix of algebraic, something maybe like x squared or something like that. It could be a trig function thrown in. We could also have some transcendental functions thrown in as well. Now when we talk about transcendental functions, what we're talking about are things like e to the x, e to the u, natural log, those types of things are transcendental functions. And usually the integration by parts is a nice mix of both of these. So let's go ahead and derive integration by parts. It is based on the product rule. So if we had two functions multiplied by each other, so if we had two functions, let's say u times v, and we wanted to take their derivative, we know the product rule would say the first times the derivative of the second plus the second times the derivative of the first. So this is just a quick application of the product rule. Now up above where we talked about products, the u and the v are the product of the different functions. Now if we look at what we have next, we could say, well, let's integrate both sides. So if we integrate the derivative, we will get the function itself back. So this would be uv right back. And then we have this piece, the uv prime, plus I'm going to look at the integral of the sum as the sum of the integrals of vu prime. Now if we apply some common notation to this, this would look like uv equals the integral of u dv. Instead of v prime, I'm just using dv, plus the integral of v, and then instead of u prime I'll use du, just as a common way to write the u prime. I want to solve for this, and so I end up with the integral of u dv is equal to uv, that's from this side, and I'll subtract this over, minus the integral of v du. This is the formula that we want for integration by parts, and again it's based on the product rule. This is something you'll definitely want to have memorized and or on your note card because we're going to be using it so often. Now depending on where and when you took Calculus 1, you may or may not be familiar with the transcendental functions that we talked about above. So here's a quick review to kind of get us all on the same page. So our quick review is the derivative with respect to x of e to the u is equal to e to the u prime. So u is some function. The derivative of e to that some function is e to the function times the derivative of the function. Let's also look at the derivative of the natural log of u. That was equal to 1 over u prime. And then we also looked at integrals. We looked at the integral of e to the u du is just e to the u plus c. We can't integrate the natural log right now. We will be able to after we get done with this lecture, but for now I don't have an integral for the natural log. However, I do have an integral for 1 over u du integrates into the natural log of the absolute value of u. So these are a quick review. If you want some more review on the transcendental functions, go ahead and go back into my Calc 1 course that's on the course website, and you can look at lots of examples on how we work those. So let's look at an example where integration by parts is going to be necessary. We'll look at one where it's not and then one where it is. Let's look at the integral of e to the 2x dx. And of course we're used to showing all of our works. U is 2x, du is 2 dx then. So if I'm trying to integrate this, I need a 1/2 on the outside, compensate with the 2 on the inside, and then I rewrite this using u substitution. Now the reason I need a 2 on the inside is I need a 2 dx, and that's right here. And then of course I have to multiply by a 1/2 on the outside because I can't arbitrarily just multiply a function by a 1/2. I have to multiply it by 1. The multiplicative identity, and 1/2 of 2 is 1. So this rewrites into 1/2 integral e to the u du. So e to the u is equal to 2x, so this integrates into 1/2 e to the 2x plus c. So this is no big deal. That's easy to do. Now what if we introduce another variable though? What if we had x e to the 2x dx? I can't integrate this anymore. Just with that one change I can no longer integrate this. So it's important that you understand taking derivatives is easy compared to integration, because integration you change one little thing and I can no longer integrate a function or it becomes extremely difficult. So if I use the same strategy here, if I chose my u to be 2x, my du would still be 2 dx then, and then when I make my substitution I have everything here. I have my 2, but this time I have this x I need to worry about. And you can see I'd have 1/2 integral, and then here's my 2 dx and my e to the u. So I'd have e to the u du, but then I have this x left over in here, and what do I do with that? I would need to switch this across somehow, and I could switch it across, I guess, by solving here. X would equal u over 2, but that still doesn't help me solve or integrate this because I'm left over with a u then. So I need to come up with some other method, and it's called integration by parts. Now with integration by parts, we look at the product, and then based on the product we kind of work from there. I abbreviate integration by parts as IBP, so you'll see IBP written down and you'll know what method we were using. Now every single time you use integration by parts, I would highly recommend you write down the general formula. The integral of u dv is equal to uv minus the integral of v du. Okay, so let's go ahead and start this problem. So a lot of times with integration by parts, we end up using something called the recursive method, which we are not on this problem, but it's important that we keep track of the left-hand side. So always write down the left-hand side of your equation as well, because at some point for some integration techniques, it's going to become very, very important that it's there. Okay, so now what we're going to do is we're going to choose a u and we're going to choose a dv. Now I have them written in this order specifically. So the u is up higher, the dv is down lower, kind of if you think about this in a grid, because I'm going to take the derivative down and then I'm going to integrate up. Okay, so there's a specific reason for this. Now, how do we choose? Well, it turns out that for our u, you have to be able to take the derivative of it, because again, we take the derivative down. So if you get a function that you can't take the derivative of, you're choosing the wrong u. Now if you have an algebraic expression involved, usually u is that algebraic expression. Now for our dv, it has to be something you can integrate, because we're going to integrate up. So in this case, with our x here, that's usually our easiest case. So if we have an algebraic function, it fits really well with our u. But we don't always have an algebraic function, so it's algebraic if possible. And then our dv sometimes is either a trig function or a trans function. Okay, so down here then we'd have e to the 2x dx. So we have to account for every single thing inside this integral. Here's my x, here's the e to the 2x dx. So the dx is important that it's there, don't drop it. So down here then, when we take our derivative, when I find my du, the derivative of x is 1 dx. Now where does the dx come into play? This was du dx, and then I multiply both sides by dx. So it's easier if you just remember it as 1 dx. Now up here, this is not as simple. V is going to be the integral of e to the 2x dx. And this requires its own little u substitution off to the side. So u is 2x, du is 2 dx. So I have a 1/2 2 e to the 2x dx would be 1/2 e to the u du, which is 1/2 e to the u is 2x. Now I don't worry about a plus c, my constant of integration, because that'll come into play a little bit later on in the problem. So this is 1/2 e to the 2x. Now, how much work? All the work. Make sure you show this off to the side and organize it. So again, for every time you do this problem, you want to write the generic uv minus the integral of v du. So I have the integral of x e to the 2x dx, and again, don't drop the left-hand side, is equal to uv, so that's 1/2 x e to the 2x minus the integral of v du. So that's 1/2 e to the 2x dx. Now, I'm not quite done yet because I still have an integral sign on the right. So now my next step is to integrate this piece. This is just a straightforward u substitution now. U is 2x, du is 2 dx, and we'll take it from there. So again, don't drop any of your work. Make sure you drag it all along because sometimes it's needed. I'm going to pull this half out front here. So I need a 2x, so I'm going to multiply by 2 on the inside, compensate with another half on the outside. So I'll write that here. And then this is e to the u du. So I have the integral of x e to the 2x dx is equal to 1/2 x e to the 2x minus 1/4 the integral of e to the u du. Well, we know the integral of e to the u is just e to the u. So we can go ahead and rewrite that as minus 1/4 e to the u. But u, we can come back up here and see was 2x. And of course, now I can add on that plus c, that constant of integration. So these are not short problems, and you have to really be careful and keep track of your work. So the things I would suggest is not to skip steps. That's going to be very important here. And also when you're working, to make sure you show all of your side work about your integrals. One thing I guess I would like to note here before I say that that's our final answer is a lot of times you want to simplify these. We're going to be looking at simplifying these because at some point we may want to take the limit, and it's easier to take the limit of when it's simplified. So here we have a common denominator. I can factor out a 1/4 e to the 2x. Factoring out a 1/4 e to the 2x, I'm just left with 2x minus 1 plus my constant of integration. So if you look at this, you can see this is a lot easier to work with instead of two terms. So simplify as much as possible when you can. On your homework, I think most of the solutions I noticed were simplified, and on the handwritten homework I'll definitely be asking you to simplify as well. So it's a good thing to get in the habit now. Now, not all problems require integration by parts, of course, but if your other methods fail, then integration by parts is another technique that you can use. So let's look at another function. Let's look at an algebraic mixed with a transcendental. Actually, let's do an algebraic mixed with a trig. And right away we can see usually we'd let u equal our argument here. Du would be dx then, and you can see I'm left over with an x, and because I'm left over with an x and I can't do my change of variable, u substitution fails. And I want to use integration by parts. So let's go ahead and look at integration by parts here. Now usually with integration by parts we choose our variable that's algebraic to be my u, and then my dv is whatever is left over. And remember, you have to account for everything here. Now you take the derivative down, so du would be the derivative of x, which is 1 dx, and then we integrate up. So to get this, we would integrate. So this is equal to the integral of secant squared of x dx, which is just a nice little antiderivative. The derivative of tangent is secant squared, so the integral of secant squared is the tangent of x. Okay, so usually I show that off to the side. I'll do that. Otherwise these get a little bit cluttered. So note, this comes from the integral of secant squared of x dx, which is just tangent of x. And this is memorized because we know it's a nice little antiderivative. I'm not going to put the plus c on there because we can use that a little bit later. So keeping track, we want to keep the left-hand side along. X secant squared of x dx is equal to, well, what is it equal to? U dv is equal to uv minus the integral of v du. Okay. I always like to write this down to remind me what I'm up to. So now I need my uv, so I take u times v, so this is going to be x tangent of x minus the integral of v du. So this will just be tangent of x dx. Now it seems like things are getting a little easier, but I'm not sure we know how to integrate tangent right off the top of our heads either. It's not like it's an antiderivative. But before we worry about integrating tangent, let's go ahead and look at our pattern here one more time. Remember, to move down here, you take the derivative. To move up, you take the integral. So that's why we have this order, because derivatives move down, integrals move up. So here, let's think about looking at our work off to the side here. Tangent is sine over cosine. So we do a u substitution here. We'd let u equal the cosine of x. And then du, the derivative of cosine, is a negative sine of x dx. So we need this negative, so we'd multiply by negative on the inside, compensate with the negative on the outside. And this rewrites negative times a negative as a positive. Cosine of x in the denominator, this would be a 1 over u. And then the negative sine x dx right here would be my du. And so this piece integrates into natural log absolute value of u, but we know what u is, it's cosine of x. So, kind of catching up here, this x tangent of x we kind of drug along. Okay, and so that was a plus. So it looks like to me we have x secant squared of x dx is equal to x tangent of x plus natural log absolute value of the cosine of x plus c. So there's my solution. Now there's not much we can do to simplify this one. There's no common denominator. There's really no like terms. So this is a pretty straightforward, nice little u sub with my tangent, and also up here, again, that's embedded inside the integration by parts problem, so these can get pretty long. So that's why you have to be really careful that you're distinctive and kind of make sure you show all your work, but organize it as well. This is going to be an important one, so make sure that you note this one. What if I wanted to integrate the natural log of x? I have no way to do that right now. However, with integration by parts, I can integrate the natural log. So note the integral of u dv is equal to uv minus the integral of v du. So I'm looking for two functions, and you're looking at this and you're thinking, I don't see a u and a dv here. I only see a natural log. But remember that we have to think about our strategy here. U I have to take the derivative of. I can take the derivative of the natural log. dv I have to integrate. I don't want to put a natural log here because I'm already trying to integrate natural log. So here will just be my dx. This will be my natural log. Now remember, we take the derivative down. The derivative of the natural log of x is 1 over x dx. And then I integrate up. And the integral of dx is just x. So the integral of dx, if you want to think about it as 1 dx, is just x. So the integral of the natural log of x dx is equal to uv. So this is x ln of x minus the integral of v du. So I have x ln of x. Now notice the x's cancel here, and I'm just left at the integral of dx, which is x. So this is a minus x plus c, my constant of integration, because this is an indefinite integral. Now this is simplified. If I wanted to, I could factor out an x. It doesn't really put it in any terms that are any easier to work with. So this would be the natural log of x, and then of course the minus 1. Is a rewrite. Now be really careful here. You have to have parentheses around the arguments of your trig functions or they'll be counted wrong. And also with your transcendental function, e to the argument doesn't need one, but the natural log of an argument needs one. So make sure you have parentheses around the arguments of all of your functions, because we want to make sure we understand that the minus 1 is not involved in this argument. And without parentheses, it's kind of hard to tell. It's ambiguous. Now sometimes when you're working with an expression, it looks like things are getting worse instead of better. So let's look at one example, x squared cosine of x dx. Now usually we'd let u equal x, du would be dx. I'm left over with an x squared, so this shows me that integration by parts might be a good thing to try. Now remember, we always write down our generic. The integral of u dv is equal to uv minus the integral of v du. So I need two functions. The u always works really well for the algebraic expression, usually, not all the time. And then our dv is equal to the cosine of x dx. So du would be 2x dx. The derivative of x squared is 2x dx. Now our v is the integral of cosine x, which is just sine of x. I don't have to make any u substitutions or anything here because I already have just my variable of x. So let's go ahead and rewrite what we have. So again, I need my uv minus integral of v du. So uv would be x squared sine of x minus the integral of 2x sine of x dx. And again, don't drop your dx's, don't drop any of that notation because it's important. It kind of gives you a clue about what's going on. Now as we look at this part's good. Now this part right here, it looks like to me I'm still left over with this x, and I don't want that. So I have to use integration by parts again. So I'm going to use u and a dv. U is still going to be my algebraic expression. dv will still be my trig expression. If I switch them back around, I'll start where I was just at the step before this. So you have to be really careful that you don't do that. This would be 2dx. V would be the integral of sine is a negative cosine. And again, that's the integral of sine of x dx. Don't forget your dx's like I just did. And then we're going to copy everything down. So this is 2 iterations of integration by parts to make this go. Now when you're doing these 2 iterations, this is the most common mistake right here, is to not distribute this negative sign. So make sure you have that involved. So I have uv, which is going to be negative 2x cosine of x minus the integral of v du. So this would be a minus 2 cosine of x dx. Now this looks like to me it's actually getting better. If you notice, my powers have gone from squared up here down to x's here, and now the x's are gone. So this is getting better. It's 2 iterations. It means I've done this twice. So the integral of x squared cosine of x dx is equal to x squared sine of x. Now negative times a negative is a positive. Now let's look here. A negative times a negative is a positive, and the integral of the cosine is equal to positive sine of x plus c. So here's my solution. Now let's look to see what's happening with my variable. It's going from x squared to x to the first to x to the 0, meaning it's gone. So it's decreasing powers, and so the highest power was 2, so I had to go through integration by parts twice. If my highest power had been 10, I would have had to go through integration by parts 10 times. And that is a little tedious. So we have a shortcut called the tabular method to help us with this. Now the tabular method is effective in a lot of different ways, but I really like it with the algebraic expression. And you can use the tabular method with algebraic expressions very easily. So the tabular method, I'm going to have these lists. And the lists always start with positive. Now we still have the same u, and what I do is I take its derivative successively until I end out at 0. So that's why you have to have an algebraic expression involved in this. You can use the tabular method for the recursive method as well, which we'll see in a little bit, but I don't recommend it because sometimes it's hard to know when to jump ship and solve. So we had dv was the cosine of x dx. So now, again, these were derivatives. Now I'm going to integrate. The integral of cosine is sine. The integral of sine is a negative cosine. The integral of a negative cosine, and I have to be careful, I'm lining these up. The integral of a negative cosine is going to be a negative sine. Then the integral of negative sine would be a positive cosine. So you can see that this is going to follow a pattern. So then my signs alternate until I run into the 0 again. And this is how I write my solution. I go across, down, across, down, across, down. So I have this product then. This would be x squared sine of x. This one would be minus 2x times a negative cosine of x. So negative times a negative is a positive. And this last one would be a negative 2 sine of x. Now if you look up here, it looks like we have everything working out, but our signs don't quite agree. So let's go back through and double check our signs. Okay, tabular method is pretty easy, so I don't think I have a mistake here. So I must have a mistake somewhere up here. Okay, so let's double check my work here. So I have a minus. Okay, so I'm doing subtraction. I put up my brackets. So this is my uv, and this is my minus integral. So here's my minus sign. I catch it. So here's v du. Now notice my v has a negative as well, so I need a negative here, not with the formula but with the sign. And then when I look at my triple negative, a negative times a negative times a negative, I should have a negative sign right here. And now they match. So that was my mistake for not double checking my signs there. And so I'm glad I checked this with the tabular method, or that error might have gone unnoticed. Now what if my power on my x squared cosine of x, what if I change that to x to the 50th cosine of x? I would have had to have done integration by parts up here 50 times, which I would not have wanted to do. So the tabular method, which I really wouldn't want to do the tabular method 50 times, would be a lot easier though, because I'd start to see my patterns and the derivatives. The numbers would get huge. But the tabular method works really well for something like that. So let's look at an example using an algebraic expression and a transcendental expression to try and figure out how kind of integration by parts really shines for some particular cases. So let's look at x to the fourth e to the 2x dx. Now, quick note, if I'm going to use a tabular method on this, I need to check for a couple things. First of all, this x to the fourth, that's going to eventually, when I take its derivative, go to 0 because I have a polynomial in the exponent. So that looks very doable. So I'm going to use integration by parts here. I'm going to use the tabular method. But I'm still going to choose my u and my dv the same way. So the integral of u dv is equal to uv minus the integral of v du. So I need to choose a u and a dv. So I need my column for my sine, u, and dv. So u, again, the easiest thing to choose is the polynomial expression, x to the fourth, and I take its derivative over and over again until I get down to 0. Now my signs will alternate starting with positive, and the reason the signs end up alternating is you can see the problems we did before, the negative sign distributes through. Now for my dv, I'm left with e to the 2x. So off to the side, let's go ahead and look at the integral of e to the 2x dx. That's a u substitution. U would be 2x. Du would be a 2 dx. So I'd multiply by a 2 on the inside, compensate with a 1/2 on the outside. So this is the integral of 1/2 e to the u du. So the integral of e to the u is e to the u, and u in this particular case is equal to 2x. So that's what goes here, 1/2 e to the 2x. So I'm going to do this over and over again. Now I'm going to integrate 1/2 e to the 2x dx. U is 2x, du is 2 dx. So I'd multiply by a 2 on the inside, compensate with the 1/2 on the outside, and I'd pull this extra half out as well. And I'd have 1/4 e to the 2x plus c. Of course, we don't need our plus c yet. So what happens is this coefficient out front just keeps getting multiplied by a half. So I'd have 1/8, 1/16, and then of course 1/32. So this is a lot easier than trying to keep track of all those signs, and in this tabular method with the table, it's a lot easier to see your sign changes and write out your solutions as well. So to start writing our solutions, this one we started out with x to the fourth e to the 2x dx. So I'm left with 1/2 x to the fourth e to the 2x. So I took care of this one. And then I have plus 1/4 times 4x cubed e to the 2x. So that's this one. Plus 1/8 times 12x squared e to the 2x. My signs have to alternate, so I have my minus now. Let's double check that. So here I had my positive. This one should have been a negative right here. Positive. Now I'm back to my negative. So this would be 24 times 1/16 x e to the 2x. And then my last one would be a plus 24 times 1/32 e to the 2x. Now obviously I have a lot of simplifying I can do here. The 1/2 x to the fourth e to the 2x I really can't do much with. On this one right here, the 4's cancel, and I'm left with minus x cubed e to the 2x plus this 12 over 8 will simplify. 4 goes into 8 twice, it goes into 12 3 times. So it'd be plus 3/2 x squared e to the 2x. We have simplification here as well. It looks like 8 can go into 16 twice and 3 times up here. So I'm going to have a minus 3/2 x e to the 2x. And of course my very end here, don't forget this little guy. So I have 8 times 4 is 32, 8 times 3 is 24. So that would be plus 3/4 e to the 2x plus c. So there's my solution, and this is a lot shorter than going through integration by parts 4 times. That's a lot to keep track of, and it leaves a lot of room for error. Now if we wanted to simplify this, it looks like we have an e to the 2x that's common. Probably wouldn't hurt to find a common denominator here as well if you want to simplify completely. So common denominator would be 4. So this would be 2 over 4. This would be 4 over 4. This would be 6 over 4. And this would be a minus 6 over 4 as well. So simplifying, I could pull out certainly a fourth and an e to the 2x. And then I'd be left with 2x to the fourth. Okay, and then over here I pulled out a fourth and I'm left with 4x cubed, so minus 4x cubed plus 6x squared. See my power is descending here, so this is working out really well. Minus x plus 3. And then in my constant of integration. So there would be my simplified form. So simplifying will come in handy because eventually I'm going to be working with limits with these again a little bit, and when I do that with integrals and I want to evaluate this, they're going to be easier to evaluate in a form where they're simplified. Now sometimes you don't have that nice mix that we've been talking about of an algebraic with a trig or an algebraic with a transcendental. And if you don't have that, integration by parts can still help you. It's just not as straightforward. So let's go ahead and look at this example where we have the integral. Let's mix a transcendental with a trig. Sine of 3x dx. So a couple things to note here. There's no polynomial factor. That means there's no x squared or x cubed to make this easy to choose for my u. And this is something of a general form, e to the x times some trig. And e to the x times some trig should, when we see it, we should need to think recursive. And I'll show you what recursive means as we're working through here. When you're using the recursive method, you usually need 2 iterations of integration by parts. Okay, so we're still going to use our formula, integral of u dv is equal to uv minus integral of v du. But now we need to choose very carefully our u and our v because we're going to be using them twice. So we have our u and our dv that we choose. Now our u can be either the e, the transcendental, or it can be the trig. It doesn't matter. I just have to make sure that whatever I choose for my u, I'm going to be able to take a derivative of it, and whatever I choose for my dv, I'm going to be able to integrate it easily. So if you choose a different u and a dv, we'll still get the same answers in the end. For my u, I'm going to choose e to the 2x, and for my dv, that will leave sine of 3x dx. Now remember, when I have my u, I have to take its derivative to find du. So that would be e to the u, u prime. So that would be e to the 2x times the derivative of 2x, which is 2 dx. And then I have to integrate up. So the integral of sine is going to be negative 1/3 cosine of 3x. Now I'm going to show my work here. I'm not going to skip any steps, so I'm going to show that kind of off to the side here. So the integral of the sine of 3x, u would be 3x, du would be a 3 dx. So I would multiply by a 3 on the inside, compensate with a 1/3 on the outside, so I have 1/3 integral of the sine of u du. Now the integral of sine, this is a nice antiderivative that we need to remember, is equal to a negative cosine. So this is negative 1/3 cosine of u, but u is equal to 3x. And so that's where this came from up here. Now with the recursive method, this is where it's so very important that I keep my left-hand side. So I'm not going to drop this on the left. I have the integral of e to the 2x sine of 3x is equal to uv, so I'll have a negative 1/3 e to the 2x, negative 1/3 e to the 2x cosine of 3x minus the integral of v. I'm going to put my negative in there this time so I don't forget it. Negative 1/3 times 2e to the 2x cosine of 3x dx. Now this actually looks a little worse, and it actually is, but it'll look a little bit better here after one more iteration. So I'm going to go ahead and drag along my left-hand side. Okay, a negative times a negative is a positive, and then I have my 2/3. Now some people would pull the 2/3 out, some people will leave it inside the integrand. It doesn't matter. So I have 2/3 e to the 2x cosine of 3x dx. Okay, so I'm going to use integration by parts again on this piece. Now when I choose my u and my dv, I really don't get to choose, I have to come up here and have a look. I used my transcendental for u before, and I need to use it again now. So I'm going to call this 2/3 e to the 2x, and then that leaves the cosine of 3x dx for my dv. Now remember that when you're using your integration by parts, I can either pull the 2/3 inside or leave it on the outside. So now take derivative down. So the derivative of e to the u is e to the u prime, so I'm going to drag along the 2/3 e to the u, and then the derivative of 2x is 2 dx, and I'll simplify that just a bit. And then over here, the integral of the cosine of 3x is 1/3 sine of 3x. Now, got to show that. So where did this come from? That came from the integral of the cosine of 3x dx. So we'd let u equal 3x, du is equal to 3 dx. So I'd multiply on the inside, compensate with a 1/3 on the outside. So this is 1/3. Integral of cosine is sine of u, but u is 3x in this case. So that's where that comes from. So we need to drag along the entire left-hand side. And again, we'll see why this is important in a moment. I cannot drop any pieces or parts here. Plus, okay. Now, what I want next is uv minus integral of v du. So I'm going to go uv. So this is 2/3 times 1/3 e to the 2x sine of 3x minus the integral of v, which is 1/3 times 2/3 e to the 2x times 2. Let's just make this a 4/3. So for this piece, we can just multiply those and make that a 4/3. So uv minus integral of v du, sine of 3x dx. Now hopefully something is starting to look a little familiar here. Let's go ahead and clean this up a little bit, make it recognizable. Don't forget my dx here. So I have a negative 1/3 e to the 2x cosine of 3x. Now a lot of times there's a minus sign right here. We don't have a minus sign this time, but when you do, you've got to have those brackets up, otherwise your signs will be wrong. And that kind of throws the whole problem off. So this would be plus 2/9 e to the 2x sine of 3x minus, okay, what do we have here? 4/9. 4/9 times the integral of e to the 2x sine of 3x dx. Okay, now it's what's on the right-hand side that looks so familiar. If you notice, on the left I have e to the 2x sine of 3x, and if you notice on the right I have the integral of e to the 2x sine of 3x as well. So I have like terms, and when you have like terms, you can solve, and I can solve by just going ahead and adding this 4/9 across, and that's why we need that left-hand side here. And I'm just balancing this equation. So if I want to think about this, this is the same as 9/9. So 9/9 plus 4/9 would give us our 13/9. So I'd have 13/9 times the integral of e to the 2x sine of 3x dx is equal to everything that's left on the right side. Now one thing that is missing is this 4/9 because we added it across, so this piece went to 0. Okay, so we're almost done. We want to solve for the integral, and so when we want to solve for the integral, what's in the way is this 13/9. So I'm going to multiply both sides through by 9/13. And of course, algebraically, we know whatever you do to one side, you have to do to the other. So these cancel, and I'm left with the integral of e to the 2x sine of 3x dx is equal to negative 1/3 times 9/13 e to the 2x cosine of 3x plus 2/9 times 9/13 e to the 2x sine of 3x. Now I'm not ready for my plus c yet because I have simplifying that still can be done. You know, actually I can see another route to the same problem. But we'll worry about that in a minute when we're simplifying it. I could have left the 9/13 out, because if we're going to simplify it, it would make sense to leave it factored out. Let's do that. I want to do that a little different. So I'm going to leave that 9/13 out front because we're going to factor it anyway. And then when I look inside here, I can see I needed a common denominator of 9. So this would be -3/9. So then I have that common denominator, and I could pull out the 1/9. So let's pull out that 1/9. And it looks like I have an e to the 2x that's common as well. So if I pull out a 1/9 e to the 2x, I'm left with a -3 cosine of 3x plus 2 sine of 3x. The 9's cancel, and I'm left with 1/13 e to the 2x. Now we usually like our leading coefficient to be positive, so I'm going to rewrite this as the 2 sine of 3x minus 3 cosine of 3x, and of course my plus c then. So I could have taken the 9/13 and distributed it like I did the first time, and then found common denominator and refactored. It just was a little extra work, so I left it factored and then worked on the inside to clarify this. So that's an example of the recursive method. It takes integration by parts twice, and you need to make sure that you leave this left-hand side of the equation out there, because if the left-hand side isn't there, you can't solve the equation because you don't have an equal sign and another side. You have to have the two sides. So again, that's an example of the recursive method. Now if you had done the same problem and you would have chosen your u and your dv opposite of what I did, we still would have gotten the same answer in the end. What you have to be careful of is when you choose your u and your dv that it's not getting worse, because not every problem can be solved with either choice with integration by parts. Now these problems are long, but I want to make sure that you get to see quite a few different types. So a few of these I'm just going to set up for you to give you some familiarity and background into some of these. Now secant cubed does not look like that it is ready to integrate at all. It does not look like integration by parts. But if I rewrite this into secant of x times secant squared of x, then I can use integration by parts on it. So this would work, and I encourage you to run through it. Integration by parts, if I let u equal secant of x, and then dv would be secant squared of x dx. Now remember, to take our derivative down, the derivative of secant is secant tangent. So secant x tangent of x dx. And the integral of secant squared is the antiderivative of secant squared is the tangent of x. So that's a nice straightforward one to do. And you can work it through from here by using your integration by parts formula. Now some problems you can apply integration by parts, but it's not necessary. But I'm going to show you how you could set up a problem using integration by parts when there's other methods available as well. So let's look at a problem, let's say like the x over the square root of x plus 10 dx. Now when I look at this problem, I wouldn't use integration by parts, I would use change of variable. And I think it would be a lot easier. We learned change of variable back in Calc 1. So we would let u equal x plus 10, du would then be dx. But then what I do is I solve for x and I'm left with u minus 10. Now the reason I do that is when I make my substitution, I'm left over with this value of x. So I could do this same problem with change of variable, or I could do the same problems with integration by parts. With integration by parts, I need a u and I need a dv. So my u would be x, my dv would be 1 over the square root of x plus 10 dx. So to me this one's a lot harder with integration by parts. The integral of x is 1 dx, and the integral of our dv, we would have to do another u substitution here. We would let u equal x plus 10, du would then be dx, and so this would look like the integral of 1 over u to the 1/2 du, and you could simplify and solve from here. So these are some examples of rewriting before you get to integration by parts, or looking at problems that integration by parts is not required but could be applied. And you have to kind of look at every problem to decide what you're going to do. My recommendation is to try the easiest methods first, and if the easier methods don't work, make sure that you look for maybe a shortcut like the tabular method with integration by parts as well, or maybe think of a rewrite. The last one I want to set up for you, and again I'm going to leave this for you to solve, I just want you to be familiar with some of these different ones, is an inverse trig function. We don't have a way to integrate an inverse trig function right now, but integration by parts can work on these. So we'd choose a u and we'd choose a dv. Now, it wouldn't make sense to put my inverse trig function here because I'd have to integrate it, and that was the original problem. So it doesn't make sense. However, I can take the derivative of an inverse trig function. Now, if I have the inverse sine of x, the only other thing that I'm left with is a dx for my dv. And then to work from here, we'd integrate up to get my x. We take the derivative down, the derivative of the inverse sine. You might have to look back or make sure you have it on a note card, is going to be the derivative of x, which is 1, over square root of 1 minus the u, or the argument squared. And then we do our uv minus the integral of v du. So that's another example of where an inverse trig function can be integrated. It's necessary to integrate it with integration by parts. There's no other method that we have right now. As usual, if you have questions, take a screenshot of your work and the problem and text it to me. I'm happy to help out. You also have the option of connecting to the Pearson tutors on My Math Lab, and they can help as well. They're available 24/7. If you're on campus, you're welcome to use the Math Center, or if you have a Math Center on your local campus as well, that would be great. Keep up the good work. These are tough, long problems, but they're really nice when they turn out good in the end.